Welcome you all to the course EC8553 Discrete Time Signal Processing. This lecture is about design of digital filter from analog filter, which is coming under unit 2. Now the topic is about conversion of analog filter into digital filter. So that time we should take care of the characteristics of the filter in the analog that should be mapped exactly in the digital. So this is your analog section, this is your digital section. This is your S plane and this is your Z plane. So in the S plane system, the pole should lies at the left side of S plane to be stable. In the Z plane system, the pole should lies inside a unit circle to be a stable system. While doing conversion from analog to digital, we should take care of all those things. The entire poles lies at the left side of S plane should be mapped inside a unit circle. The poles placed at the right side of plane will be mapped outside of the unit circle. The poles on the imaginary axis should be mapped with the exactly on the unit circle. This has to be taken care before proceeding a conversion from analog filter to digital filter. So your digital frequency ranges from minus pi to plus pi. Analog frequency ranges from minus infinity to plus infinity. So the mapping may be 1 to 1 mapping or many to 1 mapping. That depends on the methods. There are three different approaches to design IAR filter from analog filter. The first one is impulse invariant method by linear transformation, approximation, derivatives. Now we will start with impulse invariant method. So there are three important steps. So first we have to take the inverse Laplace transform to get impulse response of analog filter. Then that analog filter has to be converted into analog filter has to be converted into digital impulse response. Then take the Z transform. These are basic three steps has to be followed in impulse invariant. Okay. So we'll follow the previous slide. So let us consider a transfer function h of s is equal to c divided by s minus alpha. So the first step is to compute the inverse Laplace transform to get the impulse response. We'll have h of s here. Just do the inverse Laplace to get analog impulse response. So the inverse Laplace transform of 1 divided by s minus alpha is nothing but e to the power of alpha t. So the impulse response of the analog system is c into e power minus alpha t. The second step is we have to convert analog impulse response into digital impulse response by doing the process of sampling. So just replace t is equal to nt. So c into e to the power of minus alpha nt. Now we have to take the z transform for this h of n. Z transform of this h of n is nothing but if any signal in the form of a power n, I can write 1 by 1 minus a into z inverse. So here the corresponding z transform of h of n is c divided by 1 minus e to the power of minus alpha t into z inverse. Now the poles of this digital transfer function is e power alpha t. The poles of analog transfer function is alpha. Okay. So this is the impulse invariant formula for the first order and for the second order. This is a direct formula, so that we have to take it. So if it is in the form of 1 by s plus a, the corresponding impulse invariance is z by z minus e to the power of minus a into t, where t is nothing but sampling period. Now this is S plane to Z plane mapping, that is analog filter into digital filter. So the right side is analog system, left side is digital system. So if the frequencies from minus pi by 2 to plus pi by 2 are mapped into the upper half of the S plane, and the frequency which is beyond pi by t is also mapped on the same upper half of the S plane. Because of this, many poles are shifted to the same locations, that is called as many to one mapping. Because of this many to one mapping, there will be a aliasing effect in impulse invariant method. That's a major drawback of this concept. And now we will find what is the relationship between analog frequency and digital frequency under impulse invariance. And we know that we are going to convert h of s into h of z as per the concept of IIT. We'll take h of s simply c divided by s minus alpha, and the corresponding h of z for IIT is c divided by 1 minus e to the power of minus alpha t into z inverse. Find the poles of both analog and digital transfer function. The pole value s is equal to alpha here, z is equal to e to the power of alpha t. Now substitute the value of s in the z. So z can be rewritten as e to the power of alpha t, where alpha is nothing but s. We know that s is nothing but Laplace notation. So s is equal to sigma plus j omega. Now you can expand this exponential term e power sigma t into e power j omega t. Now z is nothing but r into e power j omega. Now it is the form of polar coordinates, so magnitude and phase component. You can equate the phase component. So this is e power j omega, this is e power j omega t. So j omega is equal to j omega t. So that is giving omega is equal to omega t. This omega is nothing but digital frequency. This omega is nothing but analog frequency. They are linearly related. This is called as linear transformation. So small omega is equal to capital omega into t, where small omega is nothing but digital frequency, capital omega is nothing but analog frequency, and t is nothing but sampling period. So the summary of impulse invariant transform method is, so the major advantage of this method is the order and stability of the analog filter will be preserved. There won't be any changes in the stability and the order of the filter. And the analog frequency and digital frequency are linearly related. But the major drawback of this method is, so there will be distortion of the shape of the frequency response due to aliasing. That aliasing occurs due to many to one mapping concept. And this impulse invariance transform method will not applicable for high pass filter and band reject filter, and some cases for band pass also, but it is highly applicable for low pass filter. The next IAR filter design method is bilinear transformation. The previous two techniques, that is approximation derivatives and impulse invariant transformation, are not highly suggested for high pass and band reject filters. So this problem will be eliminated in bilinear transformation. Okay, and this is not a linear transform, it is a non-linear transform. Now we will see how it is non-linear in the upcoming slides. And there's another major drawback in the bilinear is, so frequency warping effect. Okay, that will be eliminated by doing the process of pre-warping. So that will be discussed in the upcoming slides. Now to get the relationship between analog filter and digital filter, once again I considered analog transfer function h of s is equal to some constant b divided by s plus a. If I apply bilinear for the above transfer function, then the corresponding digital transfer function is b divided by a plus 2 by t 1 minus z inverse divided by 1 plus z inverse. Now compare both analog and digital transfer function. From this we can able to write s is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. Here I can conclude that your analog transfer function will be converted into digital transfer function by substituting s is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. Now this is s plane to z plane mapping. This is 1 to 1 mapping. So once again, similar like the previous, all the poles of the left side of S plane will be mapped inside a unit circle. The right side poles will be mapped outside the unit circle. The imaginary axis poles lies on the unit circle. Okay. And the next concept is, now we will relate the relationship between analog frequency and digital frequency for bilinear transformation. And we know that the relationship is S is equal to 2 by T 1 minus Z inverse by 1 plus Z inverse, where S is the notation for Laplace, Z is the notation for Z transform. So S can be written as sigma plus j omega, Z can be written as R into e to the power of j omega. Since we are considering unit circle, so the magnitude of R is equal to 1. So simply I have taken Z is equal to e power j omega. Substitute the values of S and Z. So sigma plus j omega is equal to 2 by T into 1 minus e to the power of minus j omega divided by 1 plus e to the power of minus j omega. Now I need the relationship between capital omega and the small omega. To get that, I am taking e power minus j omega by 2 common from the numerator and from the denominator. So I have taken e power minus j omega by 2 from 1. So I have to multiply e power plus j omega by 2, and I have taken e power minus j omega by 2 from e power minus j omega. So I have taken half of the value, remaining half will remains same, that is e power minus j omega by 2. Similarly, I can proceed for the same in the denominator also. So after taking common, I can cancel these two terms. Now the numerator looks like e power j theta minus e power minus j theta. As per Euler's rules, that is nothing but 2j sin theta. And coming to the denominator, this looks like e power j theta plus e power minus j theta, which is looks like 2 cos theta. So once again 2 will get cancels, sin omega by 2 divided by cos omega by 2, which is nothing but tan omega by 2. So capital omega is equal to 2 by T tan omega by 2. So by comparing imaginary and real terms, I am getting this. Okay. Now this is the relationship between analog frequency and digital frequency under bilinear transformation. Omega is equal to 2 by T tan omega by 2, and this is your analog frequency, this is your sampling period, the sampling time, and this is your digital frequency. So I said in the beginning slide of bilinear, this is non-linear transformation. Yeah, now we can able to see this omega and this omega are not linearly related. For the digital frequency, which is lesser than 0.3 divided by T, your capital omega and small omega are linearly related. If the frequency which is more than 0.3 by T, that time it becomes non-linear. Yeah, that is called as warping effect. For higher frequencies, however, the relationship between analog frequency and digital frequency becomes non-linear, that we discussed in the previous slide. Distortions is introduced in the frequency scale of the digital filter relative to that of analog filter. This effect is called as warping effect. This is a major drawback in the bilinear that will be eliminated by the process of pre-warping effect. Now I will explain you graphically what is warping effect. Okay, this is your analog filter response, and this is your digital filter response. Okay. Sorry, let us consider this is your analog filter and this is your digital filter, and this is a response curve for omega is equal to 2 by T tan omega by 2. These are equally spaced intervals in analog filter transfer functions. If I map these values to the digital by the process of bilinear, you can able to see the first blue color box, the length is very minimal here it is very high, but it's not an issue, that will be properly matched. And if I see the green box, then the length has been reduced. Then if I see the orange box, once again it has been reduced. Then purple, it's once again reduced, keep on reducing. So this is called as warping effect, and that's what I mentioned. Distortion is introduced in the frequency scale of the digital filter, especially it is happening only for the high frequency, not for the low frequency. Hope you understand. This is warping effect. This is a major drawback in the bilinear transform. So this is a basic comparison between impulse invariance and bilinear. So for impulse invariances, it is many to one mapping. For bilinear is 1 to 1 mapping. Impulse invariance aliasing effect may occur. It is due to many to one mapping. There is no aliasing problem in the bilinear since it is 1 to 1 mapping. And impulse invariance is not suitable to design of high pass filter and band reject filter, and some cases band pass also. But in the case of bilinear, all the type of filters can be designed, including high pass and band reject. So here in the impulse invariance, only poles of the systems can be mapped. In the case of bilinear, poles as well as zeros can be mapped. No need of warping effect in the impulse since they are linear transformation. Here frequency warping effect is present due to non-linear transform. Now the third filter design is approximation derivative. Okay, approximation derivatives by the first order approximation is they given by dy by dt is equal to y of nt minus y of n minus 1 into t whole divided by t. So we can take the Laplace transform for the above differential equations. So dy by dt is nothing but s into y of s, y of nt is nothing but y of z, y of n minus 1 into t is nothing but z inverse into y of z. We can take y of z common from the numerator. Then we can write y of s is equal s into y of s is equal to y of z into 1 minus z inverse divided by t. By comparing with analog transfer function, s can be written as 1 minus z inverse whole divided by t. Now this is the relationship between analog frequency and digital frequency under approximation derivatives. Now we can able to see the mapping between s plane to z plane for approximation derivative. The right side part indicates is s plane mapping, the left side part indicates z plane mapping. If I take analog frequency and digital frequency, it is completely merged with the radius of 1 by 2. Now the practice session for the students. So compare impulse invariant transform, bilinear transform, approximate derivatives, and make a table and give the comparison for the better understanding of these concepts. So the final conclusion is there are three different summaries. There are three different approaches to design IIR filter, that is impulse invariance, bilinear, and approximation derivatives. Among all these three, bilinear transform is nothing but 1 to 1 mapping, and impulse invariance is many to 1 mapping. Many to 1 mapping may produce aliasing effect, so but that is linear transform. In the case of BLE, it is non-linear transform, so warping effect will present. Okay, thank you for the session.